I have obtained previously an expression for a formula for the heat capacity of the gas when the volume is fixed when we heat it. I shall now calculate, assuming that the volume is fixed, I shall now calculate the increase in temperature when I switch on this heating element for the 100 seconds. Now, I found already that this heating element gives the gas a certain amount of heat. It gives the gas 2,500 joules of heat. Since I'm going to assume for now that the volume is fixed, meaning that this side of the wall is kept fixed, it's not allowed to do any to move. Right, since I already found formula for the heat capacity, I can now make use of this. Okay, so first I would need to know this change in the internal energy, since according to the first law, if there's no change in volume, there's no work done. The change in internal energy is just equal to the heat. So I'm doing it now for the case of a fixed volume, and this means that any work done would be, which we know to be pressure times change in volume. We know that this must be 0 since there's no change in the volume. So then, according to the first law, therefore, we know that the heat that goes in must be equal to the change in internal energy, because the work done as I've just found is 0. So those two are equal. And I can now use this value for the heat in here, since this increase in internal energy according to this is just the heat. I'll rearrange this to find the change in temperature. So the change in temperature, delta T, if I exchange those two, would be increase in internal energy divided by heat capacity, and increase in internal energy is the heat that goes in. Heat capacity I already know is 3/2 N R. Okay, now I need some numbers. Q we know is 2,500. R, universal gas constant, 8.31, and N is the number of moles. Now I've not got that yet, so let me say, for example, that there is 1 mole of oxygen gas here, 1 mole. So that means the N is 1. So this allows us now to find an answer. So Q is 2,500, 3/2, N is 1, and R is 8.31. So with our calculator, we can now find an answer, and the answer is 200.6 Kelvin That's the increase in temperature as a result of this heating. The 206 Kelvin increase, say from room temperature, that's about the kind of temperature you expect in an oven when you want to bake a cake or roast a chicken. So it's something that we will see in the kitchen now and then. Okay, so what I've done here is for the case when the volume is fixed. Now what I'm going to do next is this. I'm going to now let go of my hold on this side of the wall and allow it to move. I'm going to allow this to move. Okay. Now I would still want the temperature to go up by this amount, about 200 Kelvin. I want the temperature to go up by this amount. But now that I allow this side to move, now that I allow this side to move, there would be work done. There would be work done to push this piston out. So in this formula for the work done, we have a pressure times the increase in volume, and the increase in volume is not zero anymore because the hot air expands. So in order now, let's see. What I want to do is I want to allow this gas to expand, and I want to increase the temperature by the same amount, by this 200 or so Kelvin. And the problem now is that I want to find the heat that I need to put in. The heat that I need to put in now to make this happen. Okay, previously I had 2500 joules, but now that I allow the gas to expand, now they allow it to expand, I would need to put in more heat because I would need extra energy to do the work. Okay, so the plan is this. I want to find out how much heat I need this time. And if I look at the first law of thermodynamics, the heat I need to put in is the change in internal energy plus the work done. Now since I'm going to heat it up by the same temperature, the change in internal energy is the same, right? Because the internal energy of an ideal gas depends only on the temperature. So all I need, therefore, all I need to do is to find the work done and add it to the increase in internal energy, which was just the heat as we've seen just now, which was just this amount, this amount Q, which we have seen when the volume was fixed. So we already know what that is. Let me write that out. So for this problem, this is 2500 joules. That's my temperature increase. Let me write this out as well. My temperature increase is 200.6 Kelvin. Okay. Now to just make it easier, I'm just going to take it to be 200 for now. Okay, I'm just going to take it to be 200 Kelvin. But what I need to do then is to find the work done, and then I can add this up to get the heat input. So that would be the next next part of this problem. To find the work done, I need to use this formula: pressure times volume times the increase in volume. And to use this formula, I need some numbers. I need the pressure, and I need, say, the starting volume, and I would also need the ideal gas law. So for the pressure, I'm going to assume atmospheric pressure. Now, atmospheric pressure is 1.031 times 10 to the power of 5 Pascal. That's the atmospheric pressure. That's my P. Okay, so that's in Pascal. So we know we can. I'll take that as the pressure, and as the gas expands, since the outside pressure is fixed, as it expands, the pressure remains the same. So and it's the volume that is changing. So what I need to do now is to find this change in volume. So I must first find the starting volume, and then I must find the new volume. Now to find the starting volume, I can make use of the gas law. Let me first clear this. Using the gas law, PV equals to nRT. I want to find the starting volume. That means at this when it is here and at starting at room temperature. Right? I need the starting temperature as well. So I have I'm going to take this to be starting at room temperature, which I would take to be 25 degrees Celsius. Now I'm going to take I need this in Kelvin, right? In Kelvin, so I have to add 273. So in Kelvin, that would be 298 Kelvin. So that would be in Kelvin. I need the temperature. I need the number of moles, and I have that. That's the number of moles. That's N. V is what I want to find, and I need the pressure, which I already have. So given these quantities, I want to find the starting volume. And then later on, at a higher temperature, when the temperature increased by 200 Kelvin, I want to find the new volume, the expanded volume, and finally I can take the difference and find the increase in volume. So let's start. V then is equal to, divide both sides by P, nRT over P. Okay, and N is 1, R is 8.31, T is the room temperature, 298 Kelvin. And P is this value here, 1.031 times 10 to the power 5 Pascal. We'll now use my calculator. I'll find that the answer is 0.024 in volume. Units of volume is meter cubed. So that's what I will find. Now before going further, let me make a correction. Now the standard atmospheric pressure, I think it should be 1.013. So that's 1.013. I think. Okay, I'll come back to check this later. Okay, but it will make a small difference to the answer, so I'll still take it to be 0.024. And while we are here, let me just mention that if I convert this to another unit, to decimeter cubed, it would be 24 dm cubed. Alright, and let me just write down here what is 1 decimeter. 1 decimeter, not so commonly used in everyday. We have meter, kilometer, and centimeters, but hardly ever hear decimeter. 1 decimeter is 1/10 of a meter. It is also equal to 10 centimeter. And 1 decimeter cube just so happens to be 1 liter. Okay, and 1 liter is quite commonly used when you buy milk. You might want to buy 1 liter of milk. Okay, so 24 liters basically. So that's a nice number to remember. Room temperature and pressure, 24 dm cubed, is the volume for 1 mole of an ideal gas. So that's what we have in meter cubed. And this is at the room temperature at 298 Kelvin. Okay. 298 Kelvin. Now next I'm going to do it when the temperature is increased by 200 Kelvin. So this time my new temperature is going to be 298 plus 200, which is 498 Kelvin. So that's the temperature of my oven when I want to bake a cake. Right. So this time I want to find my new volume. I can use the same formula. And so on. But I can also use the relation that volume and temperature are proportional. Okay, meaning that if I double the temperature, I would double the volume. So then, if I want to find the new volume, I can do something like this. Let's say the new volume is V1. Okay, if I divide this by the old volume, then it's the same as the new temperature divided by the old temperature, because they are proportional. Okay. So this will give me that my new volume is equal to the new temperature divided by the old temperature. So that's my new temperature, okay, times the old volume. So let's do this calculation now. The new temperature is 498 Kelvin and the old temperature is 298 Kelvin, and my old volume is that 0.024. So if I multiply this, my answer is 0.040 meter cubed. So that's my new volume. Therefore, my change in volume, the delta V would be my new volume minus my old volume, meaning this one minus that one. Okay, so 0.040 minus 0.024, and the answer is 0.016 meter cubed. So with this change in volume, I can now calculate the work done, because if you remember, work done is pressure times the change in volume. And now that I know the change in volume and I also know the pressure, I can therefore find the work done. So let me do that. So therefore the work done, which is P times change in volume, is equal to 1.013 times 10 to the 5 for the pressure, times change in volume, if you recall, was 0.016 meter cubed. Multiplying these together gives 1660 joules. Okay, and when you now add this to the change in internal energy over the same temperature increase, we would find the heat that we need to heat this expanding gas up by 200 Kelvin. So write that down. So let me write down the condition. This is for a fixed pressure. Remember, I have looked at fixed volume just now. This time this is allowed to move, but there is also a condition here that the pressure is fixed, or fixed pressure. Because if the pressure can change, like maybe it changes from a sunny to a rainy day, and the pressure changes, then it will be a lot more complicated. In this case, we assume that the pressure is fixed. So for fixed pressure, the heat needed for this increase in temperature of 200 Kelvin, right? To change the temperature by 200 Kelvin, the heat needed is, according to the first law, change in internal energy plus the work done. So just copy it out again. The change in internal energy for this temperature increase I've already found earlier to be 2500 joules. And the work done I've just found to be 1660 joules. And finally, you can add this up and get the answer for the total amount of heat I need to put in from the heating coil into the gas.